Miss Jody here with another video for chemistry. I'm trying to finish up chemistry here, chapter 14 on kinetics. We do have two more chapters, chapter 15 and chapter 16. And I'm still going to do a video, even though we're going a little long here. I'm going to do a video for chapter 15 and a video for chapter 16. Just some summary points and maybe not make it as long and as detailed with calculations as the other chapters, because we are getting here towards the end and I know some are ready to be done. And usually when we're in class together, we don't always get through the entire book anyway. Sometimes we do, but sometimes with how much material is in here, trying to accomplish that in 2.5 hours each week and do the labs and make sure we have all the notes and understand all the calculations, sometimes it's hard to get through that much material. So, but of course you have the book and you can continue it at home, even with the summarized videos for 15 and 16. You can still apply that with your own particular learning at home. And you can still do the study guides and still do the, and turn those in and any of the notes that I provide. I still do want to try to get together. Students have been doing their notes on a half sheet and they're saving them for me. Some are actually going to be dropping them off at the Science Center. I'm going to make a drop box right by the front door where the dig pits are. There's a crate down there that I can open the lid and you can stick your stuff right in there, and you can just put it in like a Walmart bag or something like that with your name on it, so it doesn't, if any moisture gets in. And I'll get those glued into the empty spots in your journals. I went ahead and got all the labels ready in the spots and put some blank picture pages, and I glued in the blank tests that we hadn't taken, so they would be ready if you want to use those for review for your final exam. And I glued in some pictures just in the hopes that we could do a couple experiments. I put some picture spots in there too. I really still hope we could get together, maybe just for a week or two, and do the experiments, some of the stuff with catalyst and reaction rates, and then try to, then following week I could put all the pictures in that we take, and then you could have a pickup time for your journal the following week. Maybe have a little picnic or something. Again, who knows what's happening in our world right now and what they're going to allow us to do. And of course, that would be optional because not all parents want to even try to get back together. And I understand that. And there's also a lot of parents who want to still try to get back together. So it would be optional and you could choose that, even if it's just for us to see each other for a minute since it's been so long. So I want to still continue on and finish it up. This chapter we're on is the second part to chapter 14, which is on kinetics. And if you remember when we started talking about kinetics, it was basically the chapter before we were talking about the thermodynamic side of things. And so we found out how it worked, the thermodynamic criteria, meaning a reaction has a certain criteria it has to meet to really be considered spontaneous and be able to proceed. And so it can't defy the second law of thermodynamics. And so, in a sense, so this is helping us understand that there was a certain criteria for the thermodynamic side, but then there's also other criteria to consider, like the kinetic side, like how fast does it go? Is it the rate of the reaction? Is it slow? Is it fast? Is there something we can do to make it faster? And so we talked about like changing the temperature, and then we talked about the surface area, crushing up some of the reactants to help them to be able to collide more with, instead of being in like a solid tablet or something like the effervescent tablets or something like that. You crush it, has more surface area. And we talked about temperature, surface area, and concentration. The concentration, like if you increase the concentration, then sometimes that will increase the rate of the reaction. And so that's what we learned about the rate equation. We were talking about as the concentration changed, the rate changed on some of these experiments. And so therefore you could see that correlation between the concentration and the rate of the experiment. So we learned the rate equation. And then we did a couple calculations on that. And then now we move on to finish it up. This particular page, I wasn't going to do a whole page on it, but at first, and then I started, and then I was like, oh, do I really need to write all this out? So if you don't want to do this particular one, because it's a lot of notes for really not too much information here, but I'll still leave this page in your book. So if you just want to jot some of this stuff down, But basically, the rate order, it started talking about this earlier in the chapter, and it just said, okay, this is all about kind of the terminology, how scientists look at reactions, how they talk about it, how they put it in order. And so the order of the chemical reaction, a lot of times once we get this started putting this in the rate equation, then we figure out the exponents for it depending on, you know, the experimental data, then we would talk about this in a certain way. And X would always be talking about the order of the chemical reaction with respect to reactant A, because remember, A would be here and that would be your X exponent, and then B would be here and that would be your exponent that went with B, which would be Y. So this one would be X and that one would be Y. And so Y is the order of the chemical reaction with respect to reactant B. And then if you had X plus Y, it would be the overall order of the chemical reaction. So say, for instance, if I had this particular chemical reaction in the rate equation, I'm not trying to solve for K or anything right now. I'm just putting this in order. So I'd say this one, if I looked at this chemical reaction, I'd say first order with respect to H and O. I'd say this is first order because this would have a 1. Remember, if there's nothing there, that would really, that X coordinate or that X exponent would be 1. And so I'd say HNO2, I would say first order with respect to this. This one I'd say second order. Okay, and then the rate equation has an overall order of 3 because it would be 1 plus 2 equals 3. Now let's say it wasn't 1 and 2. What if it was 1 here and it was a 1 here? If it was 1 here and 1 there, they both would be considered in respect, they both be considered 1. So I would say that the reaction is first order with respect to each reactant. So I'd look at this and I'd say this reaction is first order, because it'd be 1 and 1 if that was the case, is first order with respect to the reactants. So that's how I talk about it, okay, in putting in order. So, but this one, it's first order and second order. But if this was 1 and 1, I'd say that both of them, with respect to the reactants, they're both first order. That would be the terminology, first order. Okay, so another thing that they point out, and this is kind of important to note down, maybe not in this much detail, but sometimes they say, sometimes when you look at chemical reactions, when you start doing the rate equation, if you have a 1 here and a 2 here, and then you look at the original equation, you might notice that that number 1 matches the coefficient that was in the original equation with this, or that number 2 matches the original, maybe the original equation had 2 Cu parentheses OH parentheses 2 in the original equation. So people start saying or thinking, oh, well, maybe this exponent number matches the coefficient of the original equation, but it doesn't always. So what you have to note is that the reaction rate orders, that's these right here, for a chemical reaction must be determined experimentally. They are not equal to the stoichiometric, who knows how I say that, coefficients in the chemical equation. So you can't always just say, oh, because in the original equation there was a 2 in front of this, so that's what my 2 will be, or there's 1. No, it's going to be determined only through experimental data, like the charts we were using, and then putting it, you know, together with figuring out how much did it increase the rate or decrease the rate. If this one doubled the rate and doubled the concentration, or whatever, this doubled the rate and doubled the concentration, that's how you got 1, or whatever. So when it comes to something like that, we have to be careful, because sometimes you look at something like, oh, that's why that's happening, but it's not. All right, and so the next one, which is more importantly the one note page, and I left a page in case we could do an experiment, and remembering the rate equation and then looking at using it. Like, okay, now that we know how to determine the rate equation, what in the world would you use it for? Okay, we got the formula, we figured it out. Okay, what does it help us with? Well, what it helps us with is if you take a look at this equation, okay, so say you have H2 in its gas form and iodine 2 in its gas form and 2 sets of HI in its gas form. And you take that and you determine a rate, okay? You use your rate equation and all that stuff, and you're like, oh, okay, I figured out this rate of the reaction. Well, what I would be looking at then is, okay, what if I had a concentration of 0.50 molar concentration, then, and I used in the iodine, I used a 0.5 molar concentration, then I would re-put this in my equation. So I have my rate, and my rate times multiplied by the concentration that I use, and then on the first one, the concentration of the second one. And then remember, this one would have a second up here, second coefficient in the rate equation here. And that would give me a rate of 0.0015 moles per second. Remember that, unit of measurement that we talked about before. And every time I start saying it, I have to go back and make sure I'm not mixing up moles and molarity. Yes, the unit is molarity. Okay, so molarity per second. So here, what I've figured out with this, using these concentrations, how does that help me? Well, what that tells me is this, because it's a time unit and a molarity unit, it's saying every second that certain amount of concentration of that reactant is being used up. It's decreasing. Okay, so when I'm using this rate equation, I'm using it to figure out, okay, when I start my reaction, the first second, this much of it is the constant of the reaction, or the concentration of the reactant is going to decrease, because as the reaction is going on, the reactants are getting used up, and then because they're getting used up, obviously because they're forming products, I can look at this rate equation and say, for that 1 second, this is the amount of the concentration of the reactant that's decreased. But here's the problem. Once I do that, see, you look at this number, you think, okay, so now I got this one number, and for the whole rest of the chemical reaction, it's happening at this same rate. No, because at this rate, the first time it happens, it's at that rate, but then you've used up some of your concentration. So now this concentration you originally had, 0.50, you don't have anymore. So now if you have a less concentration because you use some of it up that first second, you'd have to recalculate it again with the new amount you have. And then that new amount you have is not going to give you this same rate, because this equation worked with 0.5, 0.5, right? And if I take this down to whatever, how much would be used up, I'm not going to get that same number in this equation. And so each time as the reaction is going on, more of the reactants are being used up. So your rate's going to slow, because as it's being used up, then you don't have as much as you started with, so you're not going to get a higher number in how fast it's going. So if the reactant concentration decreases, so if this decreases, then the rate will go down. I'm not going to have the same rate. So it's going to start slowing the reaction down. So it might maybe say it starts fast. Then every second as it uses up more of this, it's going to slow this rate down. So it's not going to be the same across the board at all times, from the time I started the reaction to the time the reaction ended. Oh, it was happening every second, this same rate. No, it started out like that. Then I had less, and the rate went down, and the rate went down, the rate went down. And over time, like say for instance, as this would go down almost by 10, it would decrease it almost by 10 lower as it continued to go down and use up some of this. And the book gives us that example. And it says the rate is not the reaction rate throughout the entire reaction. And so you would have to continually calculate that. Now what happens is this rate that's calculated from the rate equation, the first one, is called the instantaneous rate. So as we begin, it might be really high, and this is just my bad version of a chart or a graph. They have some good graphs in our book, but say my rate is way up here, and how long it takes for my reaction. At first I have a really fast rate that is reacting, but then I use up my reactants, it gets less and less and less and less and less and less, and then my curve kind of goes down, because as time proceeds, I don't have as much to work with anymore, so my rate gets really slow. So with this concentration, if my rate's kind of slow, you know what I mean, then and I have less of it and less of it, my rate keeps going down. My rate keeps going down. Pretty soon, it looks like the reaction is not even going on anymore because I barely have any concentration left. Most of it's already turned to product, so I barely have any reactants left. So it looks as if it's totally done. But here's the thing, and this is what's hard in the chemistry world, is to wrap our mind around these concepts, because we're used to like, okay, a reaction took place and now it's over. You know, do the baking soda and vinegar, and then you put the gas gets trapped in the balloon, and eventually it stops reacting, is how you look at it. But what really happens is chemical reactions never actually finish. They just keep getting slower, till there's only like barely any product left. Any reactant left, so you don't even really notice it. It seems like it stopped, but the idea is that it still is there, just so slow, because your concentration is about to nothing, because you've used up most of it. So your rate's going to be so super slow because you barely have any of it left. So as you barely have anything left, you add it to the equation. Let's put 0.00000000000 whatever 5 with its polarity. Then you multiply that, my rate's going to be like 0.00000, you get the point. And so it's going to be so slow that it's like you wouldn't even notice it. Okay, so using that rate equation, we have to realize that the rates will not be the same the whole time. They will vary. Now, the last thing of this chapter is focusing on catalyst and reaction rates. Now, what that is going to help us with is, we've already talked about in a way to speed up these reactions, because sometimes they will be very slow and you don't want to wait around if you're trying to make some kind of chemical and you're putting two reactants together to create some sort of product, and it takes 6 years. Let's just say I'm being, over dramatic, but if it takes 6 years for a reaction to take place, how profitable is it going to be for you to be in the business of making this product? Well, every 6 years we have a batch. It takes that long. So no, that wouldn't be good. So what happens is you try to speed it up by using temperature, like we talked about before, concentration, making it more concentrated so more atoms can knock into each other and begin that process, or increasing the surface area so that there can be more touching of the atoms so that they can react, right? So those are the main ways that we would attempt to speed it up. But then there's also the world of catalysts. So catalysts, what they do is they speed up the reaction rate without actually getting used up in the chemical reaction. So that means if you're going to add a catalyst, you're going to have something that is in or is helping with the reaction without changing the end product. So it's still, in the end, you still get what you were trying to get, and it doesn't use up the product. It doesn't use up itself during that reaction. It just is helping out the reaction. So it speeds up the reaction by reducing the activation energy of a reaction. So basically, and when you think of activation energy, it's the energy it takes to get the atoms to be close to enough to each other to where then the positive and negative poles take over, and the atoms begin to break apart and rearrange into their new product form, because there's a better fit, we know, with the valence electrons and all that, or the openings. And so you're speeding up squishing them together. That's what you're doing with a catalyst. The catalyst is not going to be part of the formula in the end. The catalyst is just going to find a way to force these atoms to get close to each other, therefore causing the reaction to speed up. So there's two types of catalysts. We have a heterogeneous catalyst and homogeneous catalyst. And if we remember, these same terms were used when we learned about mixtures. Heterogeneous, hetero means different. Homogeneous, homo means same. And so when we have a heterogeneous catalyst, what that means, it is a catalyst that's in a different phase, different phase than the reactants. Just circle that in there. Okay, so different phase than the original reactants in your chemical reaction that you're taking place. So they give the example of the catalytic converter. So the catalytic converter that we have on our cars helps the reaction that normally takes place, but is way too slow. And this is the reaction. 2 carbon monoxide in its gas form reacting with 2 O2, molecular oxygen, in its gas form, will eventually produce CO2, 2 sets of CO2, right? Or 2 CO2 in its gas form. So what does that mean? Well, this will normally take place, but it's so slow, it's not going to take place fast enough when your car is putting out all this carbon monoxide, which is going to be not good for you to breathe in nor the environment. It has to be able to change it to carbon dioxide fast enough while it's in the pipe. Well, you know how long a car is and the pipes that go along with the exhaust. It's only so long. So if this is a slow reaction, you better have something speeding it up while it's moving along, or otherwise all your car is going to be putting out is carbon monoxide. So what they do is they have a ceramic structure that this is going to happen in, and it's coated with a metal catalyst. So this metal might be a platinum or rhodium or palladium. No, palladium. Who knows? So whatever it's coated with, this particular metal, what happens is this metal has the ability to attract the carbon monoxide molecules and the oxygen molecules. So because it has that pull on them, it'll attract them towards the metal, and then they will knock into each other. They will get closer to each other. So the metal itself doesn't get involved and doesn't become part of this formula. That's why it's considered a catalyst, because it doesn't get used up. It's just lining the ceramic thing, but because it has that pull, and you know how metals are, we have that metal situation all the time with the positives and the negatives, and so it's going to be attracting the carbon dioxide and the oxygen just so they can get closer, and when they get closer, they react, because that's already part of their behavior. Carbon monoxide and oxygen, O2, will want to react with each other. But most of the time, because we know how atoms are and gases, they want to spread out. And so the gases are all spread out, so you almost have to force them to get close enough so that they will react. And so they react, or they attract the molecules to the surface, forcing them to get close, and then the reaction takes place. So this speeds up. Now, the reason this is heterogeneous, right, is because we have gas, 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 and the helper of the situation, the catalyst, is a metal solid structure, right? So heterogeneous, gas, 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 solid. They are not of the same phase. Homogeneous catalyst, okay, that's going to be different. That's going to be the same phase as the reactants, okay? So you use something that's in the same phase. So if we look at this, now what's interesting about the homogeneous catalyst, they actually participate in the reaction, okay? So if we have, instead of this just kind of like pulling it near and making it force together, this particular catalyst will actually get involved, and it will be part of this process of reacting, but in the end, he won't be used up. He will still be there. So this is how it works, okay? So this particular a reaction, 2SO2 in the gas form and then O2 in its gas form will create 2SO3 in the gas form. Okay, so what you do, if it's going to be homogeneous, we're going to get a gas involved that will help do what needs to be done faster, because this is a slow process. So what they do is they take NO, not NO2, but just NO in its gas form, nitrogen oxide, and O2, I think it's nitrogen oxide, and O2 in its gas form, and they react them first. So you see in the original formula, NO is not in there. SO2 and O2. So they take the NO gas as a catalyst and add it to react with the O2. So it's going to react with the first guy. So when it does that, then it produces 2 sets of NO2. And so that is a new molecule form in its gas form. Then you take that and you take the NO2 gas and react it with this guy, SO2, and then the SO2 in its gas form, and then that will produce 2SO3, that was your original you were trying to produce in its gas form, and then a byproduct of 2NO. So this byproduct is the same guy you started with, 2 sets of NO in its gas form. So see how even though all the reaction took place to get all these things to happen faster, this guy was never used up because he came out in the end as a byproduct. And so this particular catalyst is helping speed up the reaction, but it's not using up the actual substance that was used as the catalyst. And so that would be creating the speeding up without using up. Does situation. And so in the end, when you write this out like this, where this reacts with this, and then step 2, this reacts with this to still create what we were trying to create in the first place, but we did it faster using this method than this slow old putting these two together first without any help from another gas involved. This is what we call the reaction mechanism. And so the mechanism, it's when you have those series of chemical equations that are basically telling you step by step what's actually happening in the reaction. And so this just ends our chapter in the kinetic side of things. So we figured out how to figure out the rate of the reaction, how to try to speed it up, temperature, concentration, surface area, and then of course in the catalyst world, finding a catalyst that can be part of the situation, part of the helping things become a little faster or even slower, but not being used up. And so that ends our chapter 14. And like I said, chapter 15 is going to, I think it's oxidation and reduction. Oh no, it's not oxidation and reduction. It's actual chemical equilibrium. Then chapter 16, I think, is oxidation and reaction. A reduction. Oh yes, chapter 16, oxidation and reduction reactions. All right, so hopefully you're doing well. Keep up with the work. Send, if you want to send in the study guides, you can scan those in to me, and or you can drop those off at the Science Center with any of your notes to be glued in your journal if you'd like to do that also. All right, I'll see you next time.